So with this video we're just going to look at this particular example here where we're factorising 32z to the power of 5 plus 1 into linear factors and then into real factors. So sometimes you'll get a question like that where it's just asking you either to do both or just one or the other. Now what we're going to do is to start with linear factors. Now in order to do that, first thing we recognise is that we're going to expect there to be 5 factors, 5 linear factors, because the degree of our polynomial here is 5. Now what we're going to do, and the method is to first of all let 32z to the power of 5 plus 1 equal 0. Just with our particular method, with this method, it just makes it a little bit easier. So then we're going to solve for z. So 32z to the power of 5 equals -1, which means z to the power of 5 is equal to -1 over 32. So what we've created here is an equation that's a bit like some of the other problems that we've done. Okay, so we need to solve for z. We would expect there to be 5 solutions. So we're going to use De Moivre's theorem, as we have done previously, and let z equal r theta, which means that because we're using De Moivre's theorem, z to the power of 5 will be equal to r to the power of 5 for our modulus and 5 theta for our argument. Furthermore, that's our left hand side, so on the right hand side we've got -1 over 32, which is we can also write using polar coordinates. Now it will be helpful if we just draw a little sketch here, just to get a picture of where this -1 over 32 is going to lie. Now this is obviously a real number, so it's going to be here, okay, on this side. It's the negative side. So our angle then is going to be always an odd number of pi. Because it's on the negative real axis, it's going to be an odd number of pi because it's pi around to this once. If we go around again, that's going to be 3 pi. Go around again, that's going to be 5 pi. Whereas the positive ones we've seen before are even numbers of pi. Okay, so we want odd numbers, that's really bad writing, of pi. Okay, odd numbers of pi. So what have we got? Our modulus is always going to be positive, so it's 1 over 32, but our argument is going to be 2n plus 1 pi. How did I come up with that? Well, you might remember that when we had a positive number, our first value was just an angle of 0. Well, we can't start with an angle of 0, we're starting with an angle of pi. And then we have multiples of 2 pi after that. So in order to have an odd number, we must have 2n pi plus 1, where we start with an n value of 0, so that we have 2 zeros, 0 plus 1, obviously 1 pi. That's our first position. And then it's 2 1s are 2 plus 1 is 3 pi. Our second one being 3 pi round. So what we have then is r to the power of 5 theta, for our z to the power of 5, that's going to be equal to 1 over 32 2n plus 1 pi. So that r to the 5, our modulus, is equal to 1 over 32, meaning r is equal to 1 over 2 when we take the fifth root of that. And 5 theta equals 2n plus 1 pi, which means when we divide by 5, theta is equal to 2n plus 1 over 5 pi. And that means that our value for z, which is r theta, is going to be equal to a half for our modulus, and our argument being 2n plus 1 over 5 times pi. So we're going to look at then, first of all, our value of n equaling 0. So z1, our first solution, will have a half, and 0 for 2 times n, so that's just pi on 5. We could write that as a half cis pi on 5. And this doesn't have a nice exact value for cos pi on 5 nor of sine pi on 5, so we can leave it like that. We could also write it using Euler's form as half e to the I times pi on 5. If n equals 1, then we've got z2, our second solution, being given by half, and then 3 pi on 5. So in polar form, it's half cis 3 pi on 5, or using Euler's form, it's half e to the I 3 pi on 5. If n equals 2, then we have z3, our third solution. It's a half, and then it's 2 2s are 4, plus 1 is 5 on 5, that's 1 pi, or just pi. And so that gives us a half cis pi, which we can simplify a bit more. A half times cos pi plus I sine pi, which is now cos of pi is negative 1, sine of pi is 0, so it's negative 1 times a half, so that's negative a half. And then if n equals 3, our fourth solution, given by a half, and 2 3s are 6, and 1 is 7 pi. Okay, so you can see what's happening here, the pattern involved. 1 pi on 5, 3 pi on 5, 5 pi on 5, now it's 7 pi on 5, so that's a half cis 7 pi on 5. Now, this is outside our normal argument range. If you remember, with the conjugate root theorem, we have coefficients being real numbers, so our solutions will come about in pairs, complex conjugate pairs, and so our other two solutions are actually going to work out to be negative pi on 5 and negative 3 pi on 5. But let's just have a look. 7 pi on 5 is 5 pi on 5 down to here, plus another 2 pi on 5. Okay, so 2 pi on 5 might be out here, so that's 2 pi on 5, just that little angle. That means this here is going to be negative 3 pi on 5. So this one within that range is half cis negative 3 pi on 5. And we could also write that using the Euler's form, a half e to the negative 3 pi on 5 I. And then our last one, we could work it out, but it's going to work out nicely as the complex conjugate of 5 pi on 5. So that's going to be as a result of a half 9 pi on 5, and that's going to simplify to a half cis negative pi on 5. Okay, so these are the 5 solutions. So we'll just summarise those because that actually gives us our 5 solutions. But what we've got is that we've actually got z to the power of 5 plus 1 over 32. Okay, that's what we're looking to factorise. So we can use that. That's going to be a product of these factors, z minus z1 times z minus z2 times z minus z3 times z minus z4 times z minus z5. Okay, so these are our linear factors from these solutions that we've worked out before. So that's z minus a half cis pi on 5 times z minus a half cis 3 pi on 5. Then we have the next one, z minus, or z plus rather, a half, then z minus a half cis negative 3 pi on 5, and I'll have to put it down here, times z minus a half cis of negative pi on 5. So let's group it according to their conjugates, and as we list the linear factors. So the linear factors, as the first part of the question's asking, is z minus a half cis pi on 5, z minus a half cis negative pi on 5, z minus a half cis 3 pi on 5, z minus a half cis negative 3 pi on 5, and z plus a half. So they're the linear factors. And in order to find the real factors, well, we've run out of time on this video, but the next video we'll look at how to find the real factors, and that's using what we've got over here, this formula, and we'll look at that in the next video.